So in this video, we're going to go over the runjags results, how we get them, and how we interpret them. What we're going to do is we're going to create an object called results, and we're going to do that using the runjags function. So there's a runjags function with its open parenthesis there and its closed parenthesis there. We got a whole bunch of lines, each one of these lines separated by a comma. We can draw a line through these equal signs. On the left hand side, what we have is a keyword, and on the right hand side, what we have is an option, and the keyword has to be typed in exactly as is shown here. And so we begin by specifying our model as being this object, my model. Where did that come from? Where that came from is we created this object, my model, in the last video by using the model statement. So the name we gave to our object in the model statement is the same value that we put up here. And then what are we going to monitor? What are we interested in? What we're interested in is theta. What we're interested in is theta, the proportion of the people that are right-handed. We have to put quotation marks around this thing. Now, in this particular case, I've used the concatenation function. That's what this C stands for. That wasn't necessary. But if you had more than a single variable that was being monitored, so for example, if you had two variables of interest, alpha and theta, then you'd have to put them both in quotation marks, separated by a comma, and included within the concatenation function. And then we specify the data is in this object called data for jags, which again was created in the last video. So with the handedness experiment, we had 9 successes in 10 trials. So we used the asList function to create this object called data file that's a list. And so when we looked at the structure of data file, we saw in fact that it was a list and consisted of 2 items, y equal to 9 and n is equal to 10. And then we took this data file, operated on it with the dump format function, and that creates this object called data for jags. And that's what we're seeing here. N chains stands for number of chains, and we're going to have 3 chains. Here's a chain. There's current value of theta that we monitor as we go on our random walk. So we start here, and each dot is a value of theta current. Many iterations. We connect the dots. What we get is a chain. What I'm saying here is we're going to have 3 chains running simultaneously. And that's to make sure that our model is working really well. So this is what we want to see. Ultimately, we want to see good mixing of the 3 chains. This is what we don't want to see. This is all taken from a website. This is what we don't want to see is poor mixing of the 3 chains. So we're going to have 3 chains that we're going to monitor, and in each case, we want to specify an initial value. So if this is our chain, we want to specify the starting value. We want to specify that starting value right there. And with 3 chains, we need to specify 3 starting values. Couple things. Typically, in really simple experiments like this, the choice of the initial value isn't going to make much difference, and we'll see that in a moment. Second thing is, it's generally recommended that we provide an initial value, but sometimes if we don't, R will be able to do it by itself. So, with 3 chains, we need 3 initial values. Of course, we need initial values of theta, and we use the list function to specify those. And I wanted to start off with 3 quite different values for the proportion of the people that are right-handed, 0.5, 0.7, and 0.8, just to convince myself that the initial value wouldn't have any impact on the ultimate results. Method equals parallel just allows parallel processing. Adaptation equals 1000. This is the concept of adaptation. It's quite important. Remember how we get the theta proposed. Theta proposed is equal to theta current plus delta theta. Delta theta comes from a normal distribution with mean 0, and some standard deviation sigma. The whole idea is that the choice of this sigma is not trivial. It's kind of like Goldilocks. This is in the middle. This is perfect. If sigma is chosen to be equal to 0.08, we get a nice looking chain. If sigma is chosen to be really too small, 0.01, it's rather inefficient in exploring the parameter space. Similarly, if we make sigma too big, 0.8, starts off here, lingers a while, jumps up, lingers a while, jumps around. Again, inefficient sampling. So the whole idea is we want to optimize the value of sigma. And the concept of adaptation is that internally built into runjags, it's going to explore different values of sigma to find out which one is best. And so we've said, okay, runjags, spend 1,000 iterations trying to optimize the value of sigma, and when you're done, throw those values away because we don't want those values messing up our ultimate posterior distribution. Quite different from adaptation is this notion of burn-in. So here's a bunch of iterations for the value of theta current, and what we have here is this line is the running average. Now ultimately, it's going to settle down around the running average, but for the beginning observations, even after adaptation, they're going to be quite distorted. So what we want to do is toss out a certain number of these initial observations. This is the burn-in period, so we're going to toss out the initial 1,000 observations. Autocorrelation, if you're not familiar with autocorrelation, it's worthwhile to look at the appendix. We're going to monitor autocorrelation. The whole idea about thinning is that it has been suggested that if autocorrelation is a problem, you can reduce the problem by, for example, only accepting every 5th observation. Krushke in his book says that this is not a particularly good idea, and that's why I've added this pound sign to comment it out. Sample equals 10,000. We're going to sample 10,000 observations in each chain. In other words, there's going to be 10,000 iterations in each chain. So what we have here is a bunch of options. On eClass, there's a document like this that will provide you with additional options. So that's the code to get the results. We've created this object called results. We've created this object called results in which we're going to monitor the thing of interest, which is theta, the proportion of people that are right-handed. And now we're going to look at those results. We're going to plot, again, there's the word results. We're going to plot those results. So here we see our 3 chains. And we got really good mixing. This is probably the most important panel. What is this? This is our posterior distribution. This is our statement of belief about the proportion of people that are right-handed. So there's theta, the proportion of people that are right-handed on this axis, and this is the percent total of those values of theta, and you can see that the bulk lie within this range. What we have in this panel is just the accumulation of the posterior distribution. So in other words, if I took this area under the curve from 0 to 0.6, that would be this value right here. If I took the area from 0 to 0.8, it would be this value right here. And of course, if we took 0 to 1.0, all the area here would, since this is a probability, sum up to 1.0. We've got, you can barely see it, but there's 3 different colors here corresponding to the 3 different chains, again providing indication that we get essentially identical results for the 3 different chains. This is the autocorrelation plot. Again, the appendix has some information on autocorrelation, and one of the things that it points out is that as the lag period increases, the amount of autocorrelation goes down. This is gratifying. This is what we get from runjags as our posterior. The histogram is what we got by using MCMC by hand. And the dashed line was from conjugate priors. And you can see, regardless of which method, we get the same result. We can also print this object called results. We got the median, the mean, and the mode. It's a skewed distribution. The skewed distribution, we're going to have the mode at about 848. The mean is going to be the least value, 813, and the median is going to be somewhere in the middle. Upper and 95. Upper and lower 95. Those two values define the 95% credible interval. So we've got 0.63, 0.92. This is the smallest distance that captures 95% of the probability. So if you think about odds, odds is equal to the probability that something does occur divided by the probability that something doesn't occur. Then if this is the 95% credible interval, another way to look at it is that if you were a gambler, it would be a fair bet to give 19 to 1 odds. Take that ratio, 19 to 1. That's the odds that the true value of the proportion of people that are right-handed lies between 0.63 and 0.97. The details on this other stuff are in the notes. The only thing that I want to focus on is this thing that stands for effective sample size. So if we think about sampling soils from a field, this would be random sampling, in which the samples are taken random using GPS. This would be using a random walk. So we start off here, we go on a random walk and collect samples. Because of autocorrelation, this is going to be less efficient. And you can see that here, we've got 8 samples, but they're lingering on this side of the field. So if this is the high fertility and this is low fertility, with the random walk, we're capturing too many samples from the high fertility part of the field. The whole idea is that with a random walk and autocorrelation, we lose efficiency in sampling. We had 3 chains. We had 10,000 iterations per chain, which gives us 30,000. However, because of the inefficiency involved as a consequence of autocorrelation, the number of observations we have effectively is not 30,000, but only 15,294. So that's going over the results, how they're generated, how they're produced. Really want to focus on vocabulary, things like chains and initialization, adaptation, burn-in, autocorrelation, thinning. Important ideas like the 95% credible interval and also the effective sample size.